in this example, we are given that the transformed function f of s is 1 over s times s squared plus k squared. And of course, our job is to find f of t. Now, there are actually two ways to do this problem. So we'll do method 1 first. What we're going to do is something that we've done with some of our other problems. We're going to use partial fraction decomposition. Partial fraction decomposition. So what ends up happening is this: 1 over s times s squared plus k squared breaks down as a over s plus b times s plus c all over s squared plus k squared, where k is a constant, of course. So multiplying both sides by the LCD, we end up with 1 equals a times s squared plus k squared plus b times s squared plus c times s. Solve for a, b, and c. You'll see that a is equal to 1 over k squared, b is equal to negative 1 over k squared, and c is equal to 0. So now we just have to invert. So f of t is the inverse Laplace transform of, filling in for a, b, and c, 1 over k squared over s minus 1 over k squared times s over s squared plus k squared. And remember that c was 0. So this is what we have to invert. So remember that, of course, k is a constant. The inverse Laplace transform of 1 over s is a constant 1. And you should recognize s over s squared plus k squared as being the transform of cosine. Just in place of a, we have k. So f of t ends up being 1 over k squared times the quantity 1 minus cosine of kt. That's f of t. Now, I told you that we are going to do this problem two different ways. See, method 1 is partial fraction decomposition. Method 2, we're going to use a special property that we really haven't talked about very much. The property I'm talking about is this. When you divide your transform function by s, which is the situation that we have here, okay, notice that, this is actually equal to the Laplace transform of the integral of our function u. So you have to recognize that you can take the inverse transform of big F of s. So in our situation, big F of s is 1 over s squared plus k squared. So f of t, as you know, would have to be one over k times sine of kt. Now, what we have to do is integrate. You see, we didn't have f of s. What did we have? We had f of s divided by s. So the integral from 0 to t, replace t with u of f of u du. If we were to integrate, what's going to happen? The antiderivative of sine is negative cosine. And when we integrate, we're going to get another factor of k in the denominator. Okay, so what I actually have is this negative 1 over k squared times cosine of ku, and then u goes from 0 to t. So when you plug in the limits of integration, okay, you get u be equal to t, we get negative 1 over k squared times cosine of kt, as we had before, and then minus a negative 1. So we actually get the same result. So the only problem I see with this second method, it could be a little bit confusing, okay? The small f of t that we find first is the inverse of this function, but without the dividing by s. So the dividing by s corresponds to integrating with respect to t. So again, for this problem, we could use either partial fraction decomposition, no problem, or we could use this special property of the Laplace transform. In either case, we get 1 over k squared times the quantity 1 minus cosine kt.